In the chem activity number 22 and the corresponding videos, we'll be looking at the epoxidation of alkenes. So again, alkenes is acting as nucleophiles, or pi bonds acting as nucleophiles. And in this case, we'll initially be adding a cyclical oxygen. We're going to see that several different products can be generated as a result of that intermediate. So this is kind of like the halogenation reaction where, depending on the solvent, different products can form. We're going to see that the addition will be anti. However, we'll see that whether or not the reaction is Markovnikov or anti-Markovnikov will depend on whether or not the reaction conditions are acidic or basic. We'll focus here first of all on acidic conditions. So let me introduce you to the nature of the reaction. So in order to generate an epoxide, we usually use a peroxy acid. And the peroxy acid that I will feature in this course is the M-chloroperoxybenzoic acid, which can be abbreviated as MCPBA. So I show you, first of all, a generic reaction. You take a typical alkene, you react it with MCPBA, and you form this epoxide. Now let me show you a little bit about what's so special about a peroxide. You can see that it kind of looks like a carboxylic acid, except it has two oxygens joined. And that gives it some interesting properties. So you can see I'm writing several resonance forms for this peroxy acid. One of the resonance forms shows a positive charge on one of the oxygens. Now we know that the pi bonds are acting as a nucleophile, but actually it's not that oxygen that the pi bond attacks. In fact, it's the adjacent oxygen. And this adjacent oxygen we will say is delta positive. And the other oxygen, in a sense, is involved in resonance, and so it doesn't make it a good target for a pi bond as a nucleophile. But rather this other oxygen is available, and electron density is being pulled away from that oxygen by the adjacent positive charge. So it's this oxygen here, the one that's kind of dangling off with the hydrogen, that will be the target of our pi bonds. Let's take a look. So I'm going to show you this in several steps. The first step is the generation of the epoxide. Now this will probably be the most challenging mechanism that you'll write this semester, and it is reminiscent of actually the McLafferty rearrangement. So the reaction will go in the following way, and I encourage you to always approach it in a sense in the same way, so as to, of course, arrive at the correct answer, but also to systematically approach how you're going to generate the epoxide. I'm going to start off by using the pi bonds in the carbonyl and use those in a sense as a proton transfer to grab that proton. And I can see here over on this other side that I'm going to form an OH group that's part of a carboxylic acid. The pair of electrons between the hydrogen and the oxygen will then be deposited on this oxygen, and that's the oxygen that's our delta positive oxygen that we saw in the previous slide. The bond between the two oxygens will be indeed broken. And so those steps right there will generate actually this carboxylic acid on the right-hand side. So the next stage then is, well, how do we generate the epoxide associated with the ring? And this is similar actually to the formation of our halonium ions, for instance. I'm going to first of all write in a lone pair of electrons on this delta positive oxygen. And I'm going to show first of all an attack of our pi bond onto that oxygen, and then a back attack at one of the carbons that's involved in the carbon-carbon double bond. So again, this is kind of reminiscent of our formation of the halonium ion. So that's the mechanism there to generate our epoxide. Once we have the epoxide, everything else is pretty much straightforward and similar to the reactions of, again, our halonium ion. So in step number 2, we have the epoxide, and the conditions here are for the catalytic addition of water. So you can see I've got my hydronium ions, so this means that we've got these acid conditions in water, and essentially what's going to happen to my oxygen epoxide is that the oxygen will be protonated. Now at this stage, I'd like you to imagine that the more substituted carbon is once again an example of an incipient carbocation. And again, I pick the more substituted carbon because that more substituted carbon would be more stable in terms of the incipient or hidden carbocation. And that's going to be the target of the nucleophile that we'll now attack. And the nucleophile will be our solvent, the H2O. So now we're going to have the attack at that incipient carbocation. We have to make sure that we break this next bond. Now we have added water, and it's now forming, in a sense, a protonated alcohol. Note the attack happens from the opposite side of the epoxide. So as you might imagine, this is an anti-addition, and so that's in terms of the stereochemistry. And of course, the regiochemistry is the attack of that nucleophile on the more substituted carbon. So this is an anti-addition in terms of the stereochemistry, and the regiochemistry is Markovnikov. So this is all very similar to what we've seen previously. There's obviously this last step involving water acting as a base, pulling off that proton, and now we have a diol. Note that in our diol, the two alcohols are trans to one another. And of course, that shouldn't be a surprise to you because, of course, this is an anti-addition. Now, in terms of writing out what the reaction conditions would be, so we'd say that their first step here is the formation of the epoxide. So we would write out the use of this metachloroperoxybenzoic acid, and that would be, of course, generating the epoxide. And then there would be a second step. And the second step could be written in a number of ways. For instance, we could write HClH2O, and it would be understood that the HCl is our catalyst. If you really wanted to emphasize that, you could write HCl cat and then H2O. Of course, HCl is a strong acid, and therefore it's going to ionize completely. And so we're going to have our acid catalyst in water. Water will be the primary nucleophile in this case. So that's one of the reactions associated with the epoxide. We're going to now look at a second reaction, and it's just that we're going to change the solvent a bit. So essentially it's the same reaction. And so I'm hoping that you're not feeling like there's a whole bunch of different things. They're all connected. They're all connected, first of all, the formation of the epoxide, and then it's in an acid environment. So we have a protonated oxygen of the epoxide, and then the solvent reacts.